on to our first story. So some of you have seen a site like this, maybe not this particular location. And if you're like me with a small computer screen as opposed to a huge HD projected image, as we often have, you're trying to see what in the world is the important thing in that picture. Well, the important thing in the picture is that little white dot there, and that is Venus. Venus is the nearest planet to Earth. It's the third brightest thing in the sky after the sun and moon. So it's really hard to miss. And if you've been up in the mornings before dawn, you see it. You can't miss it. It's bright, it's beautiful, it catches your eye. Some of you might remember last April during the shout out for the healthcare workers. It was brilliantly bright in the evening sky, but because the planets move in their orbits, Venus is now visible in the morning sky. So you have to get up early to see it. It'll be that way through the rest of the year, but it's a stunning sight. And for most of human history, we didn't know what it was. It was a light in the sky. So what does that mean? Well, it's been associated with the goddess Venus. And Venus, as you know, goddess of love, probably because it's so bright and eye-catching, and so celebrated in song and art. We do have a PG version in case the kids are watching. There she is, a little less of a seductress, but still having a fun time dancing in the forest. So that's our sort of societal thoughts about Venus. But of course, Venus is a world in the sky that goes around the sun. And this is kind of a cool slide because if you haven't looked at it through a telescope, you may not know that Venus has phases, just like the moon does. And you can tell from the way this drawing is that when Venus is on the far side from the sun, you see more of it being illuminated, but it's farther away. But as it comes around the bend and comes closer to us, we see less and less. We see it in a crescent form, but it's a larger planet. So that explains how we see it in the sky. Venus, of course, is a planet. As I mentioned, it's sometimes referred to as Earth's twin because it's about the same size, but it's closer to the sun and hotter. As a result, the water has boiled away. It has turned into a runaway greenhouse, and the surface of Venus is 900 degrees Fahrenheit. The atmosphere is thick and acidic. It's 90 times Earth's atmosphere, not a hospitable place. So one of the questions we like to ask is, what happened? Why did our twin become so different from us? So why are we talking about Venus tonight, other than it's bright and beautiful? It's because of this paper, Phosphine Gas in the Cloud Decks of Venus. And this got huge attention and was translated by the media as life on Venus, or maybe we should say life in Venus, because it's not on the surface, it's in the clouds of Venus. So that's another one for the 2020 bingo. And I actually really like this one that, water on Mars, everyone's been talking about Mars. Don't really care for the violence of the bus being hit by the train, but nonetheless, Venus has come barreling through as a real contender for life. So why is that? What makes us think that that is the case? Well, this paper that was published earlier this month, interestingly, was a follow-up with some of the same people who studied phosphine because they were looking for phosphine and want to look for phosphine as a chemical signature of life in extrasolar planets. We can't really see extrasolar planets very well, but we can make measurements of the chemical compositions in their atmospheres. So astrobiologists, people who are trying to learn about life beyond Earth, want to find what are the chemical signatures, the chemical fingerprint that can tell me that there might be life. So one of the signatures that was identified by this group earlier in the year, this is January 2020, recognized that phosphine, and that's phosphorus with hydrogens all around, not to be confused with phosphate, which is hydrogens with oxygens all around in an OH group, might be a signature. On Earth, phosphine is formed by life. So as I understand it, I heard a talk last Sunday from Robert Grimm, who's at Southwest Research Institute, and he had the inside skinny. I don't know this personally, but he said that they looked at Venus as a control to tell us, okay, we know there's no life on Venus, so let's measure what the phosphine levels are, expecting a part per billion or something, and then we know what an upper limit is when there's no life. We have a measure of what no life looks like. And lo and behold, that's not what they saw. They saw phosphine molecules in the atmosphere of Venus. This came as a shock to them. So actually the group publishing this is not so much a planetary science, the Venus crowd that goes and studies Venus. It's more the astrobiology crowd who were using this for control. This is what I've heard. So I hope that's true because it's a great story. So how did they do it? Well, they looked for the chemical signature spectroscopically in long wavelength, millimeter radio wavelengths at these two telescopes, at the James Clerk Maxwell telescope on Mauna Kea and at the Atacama Large millimeter array, I think it is, in Atacama Desert, Chile. And so these show you what they saw. Those wiggles are spectra. And as you can tell by the line they drew in, there's a dip there right in the middle. Now, it doesn't look very convincing, but they claim that it has enough what we call signal to noise, that it's not just noise, but that it's really there. And that's the Clerk Maxwell telescope. When you look in ALMA, it's even clearer, a very clear detection of this chemical. Now, this is really fascinating because, as I mentioned before, the phosphine molecule they tried everywhere. And they did this for the earlier paper, the January. How can you create phosphine? Can phosphine be created? And the word is abiotically, without biology. And the answer is they couldn't. They tried everything. They tried chemical reactions of different types of atmospheres and with lightning and with meteor strikes and all kinds of different ways to maybe create this molecule. And I should say, of course, the study was looking in terrestrial conditions. So the types of temperatures and pressures that you see in the terrestrial, what we call the habitable zone, planets like Earth. So very clearly, can't do it any other way. As I mentioned, on Earth, it happens from microbes, anaerobic microbes that don't live in oxygen, and also through industry. It is a byproduct of industrial processes, but those, of course, are biotic as well. So until we get to the machine age where machines are making machines. But for now, machines are being made by people. And so again, phosphine on Earth is always biotic. We mentioned that the surface is quite hostile. And so we now know that this, here's a nice little picture from Magellan of the surface, if you could strip away the thick cloud top. And in fact, we've landed a couple of missions on the surface. We humans, the Soviets did. And there's a lot of interesting history there, which if we have all kinds of time later, we might talk about. But for now, we know that the surface is completely inhospitable to life. Question, why isn't Venus a gas giant? Why aren't there any gas giants in our inner solar system? That comes from Roger. And the second one from William, fantastic question. So I'll take the first one, which is why isn't Venus a gas giant? Largely because it happened so close when the solar system was forming, close to the sun, that first of all, there wasn't as much material. Think about the circumference of Venus's orbit compared to the circumference of Jupiter's orbit, sweeping up all that material that comes together. And secondly, because as the sun was born and got hotter and hotter through the stellar formation process, it heated up and essentially blew away and boiled away all the gas that was in the inner solar system. So we didn't have all that gas to accrete and build up to be a gas giant, like the outer solar system, which was cooler and had all that gas and that long pathway to sweep up all that material. So inner solar system has all these little rocky guys like us and Venus and Mars and Mercury. Outer solar system has the big gas giants. Let me see if I want to. Yeah, I'm going to go ahead and take William's question right now because I love this question. If life is ever found, how will we know for sure? This is one of my favorite questions because you've really hit it, William, on the idea that, okay, they didn't find bugs, they didn't find cities, they didn't find, anything wiggling around. They found a molecule that through our work as chemists on Earth, we have found we could not recreate any kind of chemical pathway to make except for life in those conditions, in terrestrial planet conditions. And so I love that question because I used to, when I was a professor, ask this of my students, when would you personally be convinced? Do you need to have a conversation? When does that finally cross the threshold? And it's different from different people. Some people could care less about a bug. I personally think a bug is fabulous. I would be thrilled to have a microbe. I'd like to know if it has DNA like ours, see if we have a common chemical origin, but is just a molecule enough? It's really not. In other words, and that's why the title of the paper is not Life on Venus. The title of the paper is Phosphine Found in Venus Atmosphere. It focuses on the molecule. So then the press that went like Life on Venus. But scientists are conservative. We're not going to go into wild leaps. Actually, with that said, I'm about to say a wild leap because in our story here, we were talking about the fact that surface is incompatible. So it's thought to be life in the clouds floating around on Earth. We don't have life in our clouds. Bugs get up there, viruses float around in the atmosphere, but their origin is on surface-based life. And it circulates, but eventually will come back to the surface. There are no independent ecosystems where life is, born, lives, dies, and evolves, never touching the surface of Earth. So if that's the case, well, we have a lot to learn. So far we have phosphine. I mean, really, really begs the question, what is this? What's creating this phosphine? And what is the prediction then of what kind of life? And once you sort of infer or postulate, hypothesize what life would be like to create this, hypothesis will give you indications of your next observables. So you have to go back and study it further. First of all, this vaccine detection has to be confirmed. This is the paper. I think they sat on it for 2 years or something before publishing because they're like, I don't know. But so it has to be confirmed by other science. That's also scientific method. You can't just make stuff up. It has to be reproducible. Other people either reproduce it or don't reproduce it. And then there becomes a kind of a battle of people trying to ferret out what is actually true. So that is the next step, is to reconfirm these observations and then make predictions about what other things we ought to be able to see if this is created by life, and go look for those things. So that is a perfect example. So yeah, there are no cloud cities. There are probably bugs if they're there at all, but the main thing is they're aliens. That's a slide, if you've come to All Space Considered before, that we have used more than once. Okay, so I mentioned about not wild speculation, but here's this image that is from a Japanese mission that measures all this ultraviolet. And I also heard in this talk on Sunday, there's an ultraviolet spectroscopist who says, and this is true, that bugs, anaerobic bacteria, can absorb in the ultraviolet. So he has speculated, and I notice the use of the word between speculated, hypothesized, theorized. They all have, they're nuanced and have different meanings. He has speculated that maybe when we're looking at those dark clouds, those are just clouds of microbial colonies all floating around the atmosphere of Venus. So I wanted to share that, even though it's a speculation, just because it's kind of fun and because that's a super cool image of Venus. Okay, so just to finish up, Venus, as we said earlier, started out like Earth, but it underwent a lot of changes. There was a lot of volcanism, again, as it cooled, because it was molten. In fact, there's speculation that there's volcanism today. And as the carbon dioxide levels grew in the atmosphere and the other greenhouse gases, it just got hotter and hotter and hotter. All the water boiled away. Things, it was a runaway. It's a runaway greenhouse. And in fact, it was studying Venus that led Carl Sagan to try to draw the analogy to Earth and understand whether the same challenge would face us. So then, as I mentioned earlier, we want to go back. There are a number of missions that are slated, and NASA reacted very, very enthusiastically to this news. There's been all these missions to Mars, and Venus has been the poor cousin who just hasn't gotten the attention that Mars has. But there are some missions coming up, most notably Veritas is one of them, and Da Vinci coming up very soon. These are proposed, not, we still have a ways to go, and NASA needs to build a strategy about it. But there is no lack of competition for dollars to send us back to Venus to take those next steps and study the next bit. So has maximum temperature been established for the possibility of life? Great question. I'm not going to give you a number because I don't know that number, but we know it's more than 212 degrees Fahrenheit because we know that microbes, even though you're supposed to boil things to sterilize them, microbes can survive. They survive in the boiling mud pots of Yellowstone. So we know it's higher than that. It's not just what temperature water boils at, but at some point, molecules are pretty fragile things. You've got these atoms, think of those Tinker Toy kinds of things. You've got these atoms held together by bonds. And once it starts getting hot and they start getting jostled around through all the heat, they're gonna fall apart, and you need molecules. And in particular, life, as we know it, carbon-based life, needs these long chain molecules, and they're very fragile. So 900 is, I'm gonna go out on a limb and say 900 is too high.
Well, one interesting thing about where it's found at the top of the cloud layer, I guess that's what we're looking at, is that that's actually probably the most terrestrial type conditions anywhere in the solar system, in that if you were, say, in some kind of balloon floating there, your weight would be very similar to here on Earth. And the pressure, well, it's 100 times Earth's atmospheric pressure on the surface. It's actually the same pressure at that level, roughly 100 kilometers or so above the surface. And so the temperature and pressure are not extreme compared to Earth. It's just a carbon dioxide atmosphere, but the acid clouds and stuff are a bit lower.
Thank you. Absolutely true. Water can be liquid on the in those conditions as well. So if water is essential for life, which we think it is, then you would also have liquid water. All right, I'm gonna just finish by saying, I don't know why we need to send all these missions, because we found life on Venus, and if you want to see the footage, here it is. We never tire William Shatner here at All Space Considered. So anyway, I actually do have one more coded, and that is that, we talked a little bit earlier about Venus and the arts. Well, Venus is also celebrated in opera, and I'm going to do a little self-promotion here. I am doing a program with James Conlon, the conductor of the LA Opera, October 22nd. The tickets, which are free, but you must have a ticket so you can get in the Zoom room. They're going to put a limit on it. And it will be in the Zoom room as opposed to sent on, YouTube. They were going to do Tannhäuser this October. And we were going to have Conlon in May. You might remember we were going to do a thing about Pélias and Malzahn, because from time to time I indulge my great love of music and make some kind of lousy excuse for why this is about space. And Tony and I share that. We talk a lot about classical music together. So I'm just very excited because Tannhäuser spends the first two scenes of Act One in Venusberg, having a debauched time with Venus. Very racy, and so hey, Venusberg, that's got astronomical implications. So we're going to do this program together, October 22nd. If you like opera, or even if you don't, but I think it's going to be better if you do, because Wagner is a heavy place to start with a little opera. Then please do join us, because I think it's going to be really fun, and I'm totally excited about it.